Section 5.2, transformations of sinusoidal functions. So today we're going to graph and transform sinusoidal functions. We're going to identify domain, range, phase shift, period, amplitude, and vertical displacement of the functions. We're going to develop equations of the functions expressed in radians and degree measure from graphs and descriptions. And then we're going to recognize that there's more than one equation that can be used to represent the graph of a sinusoidal function. Okay, so new vocabulary today. Vertical displacement. Vertical displacement represents the vertical translation of a graph of a periodic function. It represents the d value of the sinusoidal function. And then we have another word called phase shift. This is the horizontal translation of a graph of a periodic function, which represents the c value of the function. So in trigonometry, rather than talking about these values as horizontal and vertical translations, we have a specific name for them where the horizontal translation is technically just called a phase shift, and the vertical translation is called vertical displacement. So for example, if I wanted to sketch the following graph, y equals sine of x plus 60 minus 1. We want to describe the transformations from the function y equals sine of x and then sketch the graph. So when we compare this, right, we would say this would have a horizontal translation or phase shift is our trigonometry terminology of 60 degrees left. And then this is a vertical translation, or we call this a vertical displacement. Of 1 unit down. So when I go to sketch the graph, I always want to start off with my base sinusoidal function, which I know has a starting point at 0, 0. It has a period of 360 and an amplitude of 1. So quite often we always want to draw 5 key points on the curve to get our sketch. So I'm just going to sketch my original y equals sine of x function, right? Because you have to have a good idea of what this function looks like before you can obviously transform it. So now I'm going to move this graph 60 units left and 1 unit down. So each of the points that I just highlighted, I'm going to go 60 left and 1 down. Okay, so my transformed function after my phase shift and vertical displacement would look like the following. Okay, and so if I continued this graph on, it might look something like this. All right, so pretty basic first example, and it's just going back to our transformation skills, but that is how you draw a sinusoidal function. All right, so in summary, this just reiterates we're going to be sketching these transformations on both a sine and cosine function. Okay, so we always want to recognize that the a value on both graphs represents the amplitude of the graph. If you're given the graph and you're asked to find the amplitude, we take the maximum minus the minimum divided by 2. If a is negative, then this is going to be a reflection in the x-axis. The absolute value of b relates to the period of the function, so it relates to it but not is equal to it. To find the period, you take 360 over b or 2 pi over b, depending on whether you're working in degrees or radians, and vice versa. If you want to find your b value, then you take the period, you take 360 degrees and divide by your period, or 2 pi divided by the period. Okay. C represents the horizontal phase shift of the function. So, right, this is going to move this starting point. This is the starting x value of the function. So we'll talk about this a little bit later. The c value is the hardest point to get because you got to think about how you got to move the graph. And then d is the vertical displacement of the function. This actually ends up representing the central axis of the function. Can be found by taking the maximum minus your amplitude. And then your range of the function, well, the minimum value will always be the vertical displacement minus the amplitude, and your max will always be the vertical displacement plus the amplitude. Okay? So, for example, if I wanted to sketch the graph y equals -3 cos of 2x minus pi over 2 plus 2. So one way you could do this is by sketching your original cosine graph and then applying transformations to this. But I actually want to get away from necessarily using transformations, and we're going to graph this by talking about these characteristics of the graph. Okay? But before I start, this section here, just like with all transformations, has to be written with your b value factored out of the expression. So I'm just going to rewrite this as 3 cos of 2. When I factor out a 2 from a pi over 2, it becomes a pi over 4. And then we have this plus 2. All right, so this is the equation I'm going to work with. So what I'm going to identify is I'm going to identify my amplitude, my period, my phase shift, our vertical displacement, technically as our central axis, and go from there. So let's start with the amplitude. Pretty straightforward. Should be 3. The period of this graph, I'm going to take 2 pi and divide it by 2. So this graph is going to repeat its pattern every pi radians. The d value tells me where my central axis is going to lie, which is at 2. And then the phase shift is going to be pi over 4 units right. All right, so what we want to do is you always want to consider your base function y equals cos of x. So our base function y equals cos of x is going to start, and its starting point would be at 0, 1. Okay? And the reason why this is an important point is because we want to figure out, well, where is this new point going to begin on our new graph? Okay? So before we begin, we're going to set up a scale that helps us so that we can graph this according to the information that we're given. So I'm going to say every 1, 2, 3, 4 units here is going to represent pi. Okay. So the first thing I'm going to do is I'm going to sketch in my central axis. So this is my central axis. Okay. Now what I'm going to do is I am going to take this original point. It needs to be stretched vertically by 3, right? Or think of this, that this point should now be technically, if I stretch it by 3, 1, 2, 3, this point would now be there. But then because our central axis at 2, I also need to move this up 2 units. Oh, sorry, this. Okay, stretch it by 3. This point would now be there. Now, because of my central axis, I'm also moving the graph up 2 units, so this point is going to become here. But then, because this is a -3, there is also a vertical reflection happening. So now I'm going to reflect this stretch it by 3, 1, 2, 1, 2, 3. Then I need to reflect it, which would be here, and then I need to move it up 2, 1, 2. So this is kind of the start point of my graph. Now I'm going to move it over my phase shift. So technically this is now my new start point. Okay, so let me reiterate that. So remember when we do transformations, stretches, reflections, translations. So my original start point is here for a cosine graph. I'm going to stretch this point by 3, which brings me to this point. I am then going to reflect this in the x-axis, which brings me to this point. So stretch, reflect. Now I'm going to translate this by moving it 1, 2 units up. This point is probably more like here. So this is my start point. Now I'm going to also move it over 1 unit. Okay, so looking at this start point, I should have an amplitude of 3, which I do. Okay, and then now I'm going to get my end point of the graph. So my end point of the graph should end up in the same vertical position after 1 cycle. And the period of our graph is 1 pi radians. So this point needs to be located at -1 again after pi radians. So that is going to occur at that point. So a full cycle is I'm going to come up and then back down within pi radians. Now I'm just going to highlight the rest of my points here. Sorry, this should be quarter pi past pi because we started here. So this would be a full pi rotation. Now I am going to figure out my other 5 key points. So we always want to plot 5 key points. We have our first 2, our starting point, our end point. Our third key point is going to be in between these 2 values at its maximum. So these are our minimum points. Our maximum, and I need an amplitude of 3. So here's my amplitude of 3. Needs to go there. And then my last 2 key points will always lie on the central axis. Again, halfway between your max and min. So my other 2 key points would be here and here. So if I were to sketch 1 cycle of this graph, it's going to look like that. Okay? It's been vertically stretched by 3, which is now our new amplitude. The period of our graph is 1 pi, so from here to here represents a full pi radians. The central axis is at 2, so halfway between your max or min is your central axis, right? Or your vertical displacement. And the entire graph is moved over 1 unit. So we're going to sketch another cycle of this. So I'm going to again draw some key points. And if we continued this cycle, that would be the second cycle, and the third cycle, and so on. So if you wanted to draw your third cycle, you could, and so on. So that is how you sketch a graph using amplitude, period, central axis, phase shift. Okay? So you get your start point, you apply all of your transformations to it, except maybe your horizontal transformation. Okay, so we stretch it, reflect it, move it, and then move it here. So that's our new starting point, and then we use our period to get this first cycle. Okay? All right, so moving on. Given information, determine the equation for a sine function that has a horizontal phase shift of 60 degrees to the left, a period of 210 degrees, and a range of -1 to 7. All right, so what we want to figure out is we want to figure out all of our values, right? Because the general function is this. So you need to figure out the a value, the b value, the c value, the d value. Well, the a value is our amplitude. So let's start with that. Our amplitude, we take the maximum, we subtract the minimum, and divide by 2. Well, if this is the range of the function, 7 is going to be the max, and -1 is going to be the min. So I'm going to take 8 minus a -1, divide that by 2. Sorry, 7 minus a -1. And I get 8 divided by 2, which is 4. So my a value is 4. I'm now going to find my b value. Well, my b value relates to the period. Because I'm working in degrees, I'm going to take 360 degrees is the original period of a sine function, and I want to divide that by 210. So my b value works out to be 12/7. My c value is the phase shift. Well, that's given to me in the question. So my phase shift is a -60 because it's to the left. And then finally, my d value is my vertical displacement. And my vertical displacement is essentially the same as the central axis. And the central axis always lies halfway between your minimum and maximum. So if I take my maximum value, which is 7, and subtract the amplitude, which is the height between the maximum and the central, I will figure out where that central axis is going to lie, which is 3. So the equation of my sine function would be 4 sine of 12/7 x plus 60 degrees plus 3. Okay. All right, example number 4. Determine the equation of the graph below as a cosine and a sine function. So this is where we can look at a graph, and technically this could be represented either as a cosine function or a sine function. Okay. Everything is essentially going to be the same except for your phase shift. Okay, so let's talk about things that are happening in this graph. Okay, so let's first talk about our amplitude. Okay, so our amplitude can be found by taking our maximum minus the minimum divided by 2. So our amplitude is 3. Our b value is found by the period. So what I want to do is I want to sketch one, and I always start on the y-axis. I'm going to sketch one rotation. Start on the y-axis if it's convenient. If not, then find 2 other points that's easy to start from. But if I draw one cycle of this graph, my period is 2 pi. So my b value would be the period is 4 pi. So I'm going to take 2 pi divided by 4 pi. My b value works out to be 1/2. C value, we're going to come back to this. And then my d value is my central axis. Well, you can kind of gauge where your central axis is if I were to sketch it in, right? It's the halfway point. Or if you take 7 and subtract, so you take your maximum minus your amplitude, that will also give you your central axis. All right, so the phase shift's a little tricky because depending on the function you're working with, it's going to be different. So the easier one is the cosine function. So what I want to imagine is I want to think about my original cosine function. Right? This starting point on my y-axis starts at the maximum. So all you want to look for is how many units did that move over from your y-axis? Where is the maximum located now? So if I take a look, here's my maximum point, it's moved off of the y-axis by half a pi. So for a cosine function, c value would be half a pi. Sine function's a little bit tricky, so now I want to visualize what our sine function looks like. So the sine function normally starts at 0, 0. It comes up and around. So technically my start point of my function starts at the central axis, and the curve of the graph starts in a direction of going up. So you want to look for that same direction off your central axis to get your phase shift. So if I look on my central axis, we kind of have 3 key points here, right? And we always want to pick the one closest to the y-axis. So this would not be a phase shift because the graph at the central axis is going down, and we are looking for this shape. We're looking for, at the central axis, where does my graph begin to start going up? And this would be my key point. Okay? It could be this, but this is too far away from the y-axis, so you always want to pick the closest one to the y-axis. So here, this would be a negative pi over 2. So for the sine function, the phase shift would be a negative pi over 2. Or if you chose 3 pi over 2, that technically is not wrong. If you chose this point, technically it's not wrong, but generally as an equation we always write the first one closest to the y-axis. So our equations for these two functions would be y equals, our amplitude, our a value is 3, cos of our b value is 1/2, x minus pi over 2, and then plus 4. Our sine function would be similar, 3 sine of 1/2. So all these values are the same. The only thing that's changing is our phase shift. This is going to be x plus pi over 2 plus 4. And if you did write it with the further phase shift, that would not necessarily be wrong. Plus 4. Okay, so those would be the equations of this graph. All right, moving on to example number 5. It says the first maximum occurs at 2, 8. The first minimum occurs at 6, 2. Determine the period, amplitude, and central axis. So what I want to do is I want to get a quick little sketch of these points in terms of our sinusoidal function. So at 2, 8, this tells us this is our first maximum. And then it tells us that 6, 2 is our first minimum. So this is kind of the start of our graph here. Right? Determine the period, amplitude, and central axis. Well, technically the period represents the horizontal distance that it takes to complete one rotation. So if it took 4 units to complete half a rotation, then it's going to take another 4 units to complete the full rotation. So this entire span from 2 to 10 would be 8. So the period of my function would be 8. The amplitude, so you can simply use that formula, max minus the min divided by 2. The amplitude should be 3. And your central axis is the same as your vertical displacement, which if you would sketch it and draw it in, or you can simply take the maximum, which is 8, and subtract your amplitude, which is 3. Central axis should occur at 5. Okay? All right, and then last example. Determine the characteristics of the following Graphs, if you're given the function y equals 6 cos of 2x minus pi over 2 plus 2. So before we can talk mainly about the phase shift, we need to rewrite this equation so our b value is factored out, just like we've done with all of our transformations.